In this lecture series, we'll be looking at 3 reactions of alkynes, 2 of which we've already seen for alkenes, the hydroboration oxidation reaction and hydrogenation reactions. Those 2 reaction classes will be the focus of this lecture video. As we saw previously, the hydroboration oxidation of alkenes generates alcohols. But because the hydroboration oxidation of an alkyne will generate an unstable alcohol, an enol, these hydroboration oxidation reactions will instead form ketones and aldehydes as the final products. More specifically, the hydroboration oxidation reaction of internal alkynes will form ketones, and the hydroboration oxidation reaction of terminal alkynes will form aldehydes. And this difference in products for internal and terminal alkynes results from the anti-Markovnikov regioselectivity of the hydroboration oxidation reaction. Let's take a look at that in more detail. The reaction begins in the same fashion as the reaction of alkenes with borane. The nucleophilic alkyne attacks the electrophilic boron at the less substituted carbon, and in a single concerted step, the hydride transfers to the more substituted carbon of the alkyne. Then in step 2 of the reaction, the borane is replaced with an alcohol by the hydrogen peroxide and base. This step results in the hydrated product, which is an enol. And remember, we saw in the last lecture video that these enols aren't very stable and will undergo a rearrangement or tautomerization to form the ketone. We won't draw out the mechanism in detail here, so review it again if you need to, but remember that the only atom that moves is the hydrogen. So the carbonyl will be in the same position or on the same carbon as the alcohol group was in the enol. This was an example with a symmetrical internal alkyne. If instead we have a terminal alkyne, then the reaction will form an aldehyde, as we'll see on the next slide. As we've seen, the addition of borane, or BH3, to an alkene or alkyne will always occur with anti-Markovnikov selectivity. It will place the BH2 group on the less substituted carbon and the hydrogen on the more substituted carbon. That means that the addition of borane to a terminal alkyne will place the BH2 group on the terminal carbon, the alkyne bearing the hydrogen. The reaction begins with the nucleophilic alkyne attacking the electrophilic borane to place the boron on the less substituted carbon. I like to count my carbons in the starting material and the product to make sure that I have the right number of carbons and to make sure that I draw the alkene in the right place, in the same position as the alkyne. Here that's carbons 1 and 2. In the second step of the reaction, hydrogen peroxide and hydroxide replace the BH2 group with an OH. This gives us the enol intermediate. And remember, as we saw previously, this enol is unstable and will tautomerize or rearrange to form a carbonyl product. And here, because the carbon bearing the OH contains a hydrogen as the other group, the carbonyl formed from tautomerization will be an aldehyde instead of a ketone. And if that's at all hard to see, then take a moment and draw out the full tautomerization mechanism that we learned previously in order to convince yourself. The second class of reactions we'll see in this video are the reductions or hydrogenations of alkynes. And remember that we saw that alkenes are reduced by palladium on carbon. So are alkynes. So if we treat an alkyne with hydrogen gas, or H2, along with palladium on carbon, the alkyne will be reduced to the alkene, and the alkene will be reduced to the alkane. So palladium on carbon will generate an alkane product from the alkyne. But sometimes we might want to reduce an alkyne and stop at the alkene. And to do that, we have 2 different sets of reduction conditions that we can use. One that will generate the cis alkene preferentially, and the other will generate the trans alkene preferentially. To generate the cis alkene, we use what's called Lindlar's catalyst. And Lindlar's catalyst is palladium metal on calcium carbonate that's been treated with lead acetate and quinone. And all that means for us is that it's a deactivated or poisoned catalyst that functions like palladium on carbon. The alkyne binds, and reduction occurs at a single face of the alkyne to place both hydrogens on the same side of the alkene, giving the cis-alkene product. But because the catalyst is deactivated, it's not strong enough to reduce the alkene product to the alkane. So the reaction stops at the alkene. To generate the trans-alkene, we use a dissolving metal reduction. And these are conditions that use sodium metal or lithium dissolved in ammonia. And these conditions basically generate stabilized electrons in solution. An electron adds to the alkyne and initiates a radical reaction to add 2 hydrogens from ammonia across the alkyne. And because it's a radical reaction, there is no inherent selectivity, so the trans product forms preferentially because it's the most stable product. Remember that trans alkenes are more stable or have a lower energy than cis alkenes. Let's end this video with a quick concept check. What products would be formed from each of the reduction reactions shown? In the first reaction, the conditions using palladium on carbon with hydrogen gas, both the alkene and the alkyne will be reduced, and they will both be reduced down to the alkane. That means that to draw the product, we just need to make sure we have the right number of carbons, and we include any groups like the methyl group in the correct positions. In the second reaction, Lindlar's catalyst will give a selective reduction, reducing only the alkyne. And because it occurs on the metal surface, it will occur with syn stereochemistry to give the cis-alkene. So again, I want to keep track of the number of carbons and make sure that I leave the alkene untouched. And then in place of the alkyne, I will draw a cis-alkene. In the final reaction, the dissolving metal reduction, again, only the alkyne will be reduced. But here it will be reduced to form a trans-alkene, the more stable alkene, because these conditions generate radical intermediates, and the radical reaction has no inherent selectivity. The selectivity favors the more stable product. So once again, I'll keep track of the number of carbons, make sure I leave the alkene untouched, and then in place of the alkyne, I will draw a trans-alkene.